What specific problem does the proposed method aim to solve regarding sparsity in large language models?
The proposed method aims to address two significant challenges in achieving effective sparsity in large language models, LLMs. Firstly, it tackles the issue of insufficient representation in small calibration sets, which fail to capture the extensive knowledge embedded in LLMs, limiting the generalizability of pruned models across diverse domains. Secondly, it confronts the inaccuracies arising from using handcrafted importance criteria as proxies for true discrepancies caused by pruning, which can lead to suboptimal mask selections. By introducing a learnable framework that employs end-to-end training on large-scale datasets, the method optimizes mask distributions to maintain the original quality of dense LLMs while facilitating the learning of domain-specific masks. This approach not only enhances the accuracy of mask selection, but also enables efficient transfer learning of sparsity patterns across different tasks.
How does the proposed method for semi-structured pruning work? Illustrate the process step by step, including any key components like Gumbel softmax.
The proposed method for semi-structured pruning operates through a learnable framework that focuses on NM sparsity, specifically targeting the selection of optimal masks for large language models, LLMs. First, it formulates the mask selection as a probabilistic sampling problem, where each candidate mask is associated with a probability distribution. To facilitate differentiable sampling, the method employs the Gumbel softmax technique, which re-parameterizes the randomness of sampling into an independent variable, allowing for gradient-based optimization of mask probabilities. During training, the model samples masks from this distribution, adjusting the probabilities based on the quality of the sampled masks, thereby refining the mask selection process iteratively. Additionally, the method incorporates sparse weight regularization to maintain the magnitude of remaining weights, which is crucial for effective mask learning and transfer to downstream tasks, ensuring that the pruned model retains its performance.
Can you provide a practical example to demonstrate how the mask selection and sampling process occurs in your proposed algorithm?
In our proposed algorithm, the mask selection and sampling process is exemplified through the handling of a parameter block consisting of 4 parameters, denoted as W in math BB_R1 times 4. For a 2 to 4 sparsity configuration, the goal is to identify an optimal binary mask, m** in 01*1 times 4, that contains exactly 2 zeros, resulting in a candidate set of 6 possible masks. To facilitate the selection, we define a categorical distribution with probabilities assigned to each candidate mask, which are adjusted based on their performance during random sampling. By employing the Gumbel softmax technique, we can sample from this distribution in a differentiable manner, allowing us to optimize the probabilities of the masks through gradient descent. This process iteratively refines the mask selection, ensuring that the sampled masks maintain the original quality of the dense LLM while effectively exploring the candidate space.
What are the main advantages of using your learnable mask method compared to existing approaches such as Sparsity and Wanda?
The main advantages of our learnable mask method compared to existing approaches like Sparsity and Wanda include improved accuracy in mask selection and enhanced scalability to large datasets. Our method directly optimizes the language modeling loss during end-to-end training, which addresses the inaccuracies in importance metrics that plague one-shot methods. For instance, our approach achieved a perplexity PPL of 6.72 on the Llama 2.7b model, significantly better than Sparsity's PPL of 10.42, without updating the LLM parameters. Additionally, our method effectively scales with the number of training samples, consistently improving mask quality even with large datasets, while existing methods show diminishing returns beyond a limited calibration set size. Finally, the incorporation of prior masks allows for efficient transfer learning, further enhancing the quality of learned masks across different tasks and domains.
Explain the validation process of your method. What datasets and metrics were used to demonstrate its effectiveness, and how do the results compare to baseline methods?
The validation process of our method involved evaluating its performance on several large language models, including Llama 2 7B, Llama 2 13B, Nemotron 415B, and two in-house models, GPT-3 843M and GPT-3 2B. We utilized the C4 dataset for one-shot pruning and the Wikitext dataset for evaluation, employing the LM-eval harness for zero-shot evaluation. The effectiveness of our method was demonstrated through the perplexity (PPL) metric, where our approach achieved a PPL of 6.72 on the Llama 2 7B model, significantly outperforming the baseline method Sparsity, which recorded a PPL of 10.42. Additionally, our method showed superior scalability, as it consistently improved mask quality with an increasing number of samples, unlike existing methods that plateaued beyond a certain calibration set size. Overall, the results indicate that our Learnable method not only enhances performance, but also effectively addresses the limitations of previous approaches.
What are some limitations or potential challenges of your proposed method that you identified, and how might these impact its applicability in real-world scenarios?
One limitation of our proposed method is the potential for gradient vanishing during mask learning, particularly when pruning leads to zero parameters in the network, which can adversely affect downstream transfer and fine-tuning. Additionally, while our method effectively scales to large datasets, it may still struggle with learning accurate masks in a limited number of training steps due to the massive parameter scale of LLMs. The reliance on prior masks for initialization, while beneficial, may also introduce biases if the pre-computed masks are not representative of the target domain. Furthermore, the stochastic nature of the Gumbel softmax sampling process can lead to slow convergence if not properly managed, as an inappropriate scaling factor may either overfit to certain masks or explore too broadly. These challenges could hinder the method's efficiency and effectiveness in real-world applications where rapid adaptation and high-quality performance are critical.